Recording. This will be recorded, and we are putting this up on our YouTube channel.
Cool.
We can give you can either link to the send a link to the YouTube channel, or we can actually give you the video and you can mirror it on AOT's website or whatever. Whatever
right.
you'd like to do.
No big deal.
Okay. Howdy, y'all, and welcome to Evening Under the Stars. My name is Dr. Rob Parks, and I'm the Deputy Director here at the George Mason University Observatory. And we have our lovely guest, Dr. or Proto-Doctor Courtney Crawford. She is not a doctor yet, but she will be very soon. And she will be giving us a wonderful talk on Aurora. But before I get into that, I just wanted to introduce the observatory and the proceedings for this evening, assuming that I can tech and actually make things go. Yay, I made things go. So today we're fortunate enough that the weather here in Fairfax is cooperating quite nicely. It is only a little bit of high cirrus, so for the most part very clear, so we'll be able to show you some of the nice views of the sky, including the Orion Nebula. Pictures of which in the upper left you can see is a picture of the Orion Nebula taken by one of the students here at GMU, along with other astronomical bodies. The observatory itself is located on Research Hall, specifically the Silver Tower, adjoined to Research Hall, and then our control room is located on the roof right beside it. Right now, a couple of our graduate students are diligently working with the telescope and getting it up and running so that we can use it for tonight's festivities. Evening Under the Stars is a lecture series that we do or attempt to do every semester over fall and spring. This spring, the Evening Under the Star lectures will be every alternating Tuesday for the most part. If you go to the website, Evening Under the Stars, there will be a list of future dates. I believe the next one is March 1st. And the talks are, the Evening Under the Stars proceed with a 30 to 45 minute public talk about some astronomically related topic. And then there is roughly around a 10 to 15 minute Q&A session. And then afterward, we give a 30-minute guided tour. Now in the before times, we would do this in person. As you can see from the slide, we would have people meet in our auditorium for the public lecture and meet up on the roof and use our variety of telescopes to view the night sky. The the positive side of being virtual is we are able to actually get folks from all around the country to give us talks like Courtney tonight. But hopefully, eventually, we will be going back to the in-person tours, and we will have you all here at the observatory and looking through eyepieces as you should. If you're interested in what we do here at the observatory, or just interested in space news in general, I would ask that you subscribe to our newsletter, or the Moon, the Mason Observatory Outreach Newsletter. It talks about not just the observatory, but our public outreach, what our students are doing, both from a research perspective and from just a student perspective. And we also talk about public nights or opportunities folks can have to look at the night sky in conjunction with the Northern Virginia Astronomy Club. Words are hard. If you're really interested in or if you're really excited about what we do here at the observatory, I would ask that you consider becoming a patron of the observatory. We here are attempting to greatly expand the amount of outreach that we've been doing. We have accelerated the number of tours, of private tours that we do almost by 10-fold. And we have been doing and then we have also been moving to other locations, visiting folks with our inflatable planetarium and producing shows in that way, and expanding and introducing astronomy to a younger audience that way. All of that, of course, requires some funding in order to provide our tour guides with the necessary funds to help compensate them for their time and effort in doing so. So if you're interested in that sort of thing and would like to help us out, I very much would appreciate if you consider becoming a patron of the observatory. You can do so at all number of levels, from Star all the way to Big Bang, which is a lifetime membership. If you have a couple million laying around, we'll even name the telescope after you. The Mason Observatory is not a one-person show. Professor Peter Plavchan is the director. I am the deputy director. Currently, Kevin and Em are observatory graduates, TAs, are, as I said, working on the roof with our telescope, getting it into shape for tonight's observations. We also have a number of students who are part of the Friends of the Observatory student organization and tour guides who assist us greatly in not only events like this one, but as I said, those public tours that we have, and also for those events where we go out with telescopes or planetarium and greet the public that way. All right. Now, let me introduce my guest, Dr. Courtney Crawford. She is currently a grad student at Louisiana State University, but she is going to be graduating very soon and proceeding in her career, her postdoctoral career in astroseismology in Sydney, Australia. I am very excited to have her here. She's a friend of mine that I met at Louisiana State when I was there a few years ago. She will be talking about the wonders of aurorae, not just on the Earth, but also in the solar system, Jupiter, Saturn, and so forth. So without further ado, I'll stop my rambling.
All right.
Courtney, if you want to take over.
Let's get going. All right. Are we good? You can see me?
Yep.
Okay. Yes. So hello, I am Courtney Crawford. I am a graduate student at LSU, preparing to defend my dissertation in a month or so. But today I'm going to talk to you about something that I don't even research. I just think they're really neat. So I want to talk to you today about auroras on Earth and elsewhere. Before I talk about anything, I want to just say that as for the plural of aurora, I believe auroras and aurorae are both correct, and I will use both. So I usually mean the plural if I'm talking about multiple. Okay, so I also want to dedicate this talk to Dr. Arlo Landel. He was an emeritus professor at LSU. He passed away just a few weeks ago, and he was a great man, but he was well known for a lot of things in astronomy. And one of the first things he ever did when he was a graduate student was in 1957, he actually overwintered in Antarctica, specifically to study the southern aurora. So I thought I would just dedicate this talk to him because I gave it originally to impress him. So I hope you know that he enjoys my talk. Anyways, let's get started. Auroras on Earth. Auroras on Earth are the one that we really know about. Aurora is just the fancy Latin name for the northern lights usually, although there are also the southern lights. So I'll start from the beginning. How does this actually work? What is an aurora? Where does the light come from? So I'll take you on a story of a little particle from the sun as it becomes an aurora. The light comes from the sun originally, as does all light on Earth. So when you have this, the sun is always sort of emanating this solar wind, and these are kind of just like particles from the sun that are blowing away. But sometimes the sun will have these little bubbles of material that come off, and those are called solar flares or sometimes coronal mass ejections. And here's an example of one where you can see that basically a bubble of material from the sun is just sort of billowing away from it. And when those little bubbles of material start coming towards us, what happens is they get caught up in our magnetic field, the Earth's magnetic field. So since the Earth has an iron has a molten liquid center that's full of a lot of metals, especially iron. Those moving metals have an electric current associated with them. And so that then induces a magnetic field around the Earth. So that's why we have a magnetic field at all. But as the sun's material comes towards the Earth, it sort of gets caught in our magnetic field. So this big outer blue magnetic field line is what's called the magnetic shield. And it's really effective at protecting the Earth from the most harmful of solar winds. But sometimes when there's a really big like coronal mass ejection or solar flare, what can happen is the solar flare will disrupt our magnetic field just a little bit, and it'll be able to tunnel in towards the poles of the Earth in the north and south side. So as it tunnels in, as this material from the sun tunnels in towards the Earth's poles, what happens is those electrons, which are charged particles, get caught up in the magnetic field and start spiraling around this magnetic field line towards our poles. And when electrons are going really fast and spiraling around these magnetic fields, they have a lot of energy. And when the energy from those electrons that are spinning really fast and spiraling bump into material in our atmosphere, it actually excites the material in our atmosphere. I want to just mention that there is a label here, synchrotron radiation. So radiation is just light. And so the spiraling electrons do create their own radiation. However, this is not the aurora. This is a radio wavelength of light. So we would be able to detect this, but it's not the aurora that you're going to see with your eyes. The aurora comes from the electrons bumping into material in our atmosphere. So in our atmosphere, we have a lot of different layers of material. You may be familiar with these sort of labels: troposphere, stratosphere, mesosphere. But the outermost two layers of the atmosphere are also called the ionosphere, and they're full of charged particles. So basically an ion is any particle that has either a positive or negative charge. So these spiraling electrons that are on these magnetic field lines excite the ions in the ionosphere. So when you excite something, you just make it really energetic. You impart energy into that atom. And when you have a high energy atom, the atom has nothing to do except to relax back down to its main, what we call a ground state, or just a lower energy level state. So this here is a model of an atom. If you're familiar with the Bohr model of the atom, this is a good example of that. And it's really good at explaining how emission works. So we have an energized atom here. So here's the nucleus and then the electron around it. The electron is in some high energy level state. This is what this outside circle is. But when it relaxes, it loses some energy, and that electron jumps back down to a lower energy level. And when it does that, it has to emit some energy. It has to let go of the energy that it doesn't need anymore. And that energy will come off in the form of light. It'll come off in the form of a photon. And the color of that light, the wavelength of that light, is very specific to what kind of atom is doing the relaxing, what kind of atom was energized and then relaxed back down. So those colors usually tell you what element is actually doing the emission. So here is a picture that looks fairly complicated, but it's going to help summarize everything that I just said, right? So we've got the sun, which is constantly giving off this solar wind. And then sometimes it will let off a solar flare or a coronal mass ejection. And the material from these little, what I'm calling sun bubbles, when the bubbles come off the sun, will travel with the solar wind and get to the Earth, come in through its magnetic shield, pass through its magnetic shield, and in towards the two poles of the Earth. So if you see the material that gets caught up in the northern hemisphere creates the aurora borealis, or the northern lights, the northern aurora. And the stuff that comes in through the southern hemisphere creates the aurora australis, or the southern lights, or just the southern aurora. So all of that material is coming in through the two poles, and the aurora that actually occurs in this little area called the Aurora Oval here, which is labeled on both sides. The Aurora Oval is the same on the north and southern sides of the hemisphere. If you remember me talking about Arlo, what he was actually studying when he was in Antarctica was whether or not the southern lights and the northern lights were the same. And he was one of the first people to find that, yes, they are the same. Anything that happens in the northern hemisphere, when it relates to aurora, is going to also happen in the southern hemisphere. They occur at the same time. So this auroral oval is where your aurora is actually going to happen in the sky. It's usually around 60 to 70 degrees in latitude. So that's same on the other side, but in, -60, -70. But as you increase solar activity, you actually increase this value called Kp. It's just a measure of the solar activity, the magnetic activity. And the auroral oval will move down the Earth, down towards the equator. And so if you have very high levels of solar activity, you can see aurora even lower on the Earth. And in fact, in November of this past year, we had an aurora that corresponded to a Kp of 8. So we were having a lot of reports of people seeing aurorae up in this sort of area, up in the northern to mid US. In fact, you can look this up and there's a whole lot of people who posted pictures of it. They're really cool. Okay, so the auroral zone moves around based on how much solar activity you have. So that's pretty neat. In fact, there are some really historical events which are quite interesting. And the biggest event of such event is called the Carrington event, the most commonly known at least. So on September 1st of 1859, Dr. Carrington observed a very, very bright solar flare on the sun. And this was in fact one of the first ever recorded solar flares. So that's really cool. It was very bright. And in fact, the next day, there was a huge aurora that was observed on Earth. And it was one of the first big aurora that was documented. They mentioned seeing auroras at 20 degrees latitude. So I'm in Louisiana, which is at plus 33, and it would be even lower than that, lower on the Earth. So that's actually bananas. That's so strong. That's a really crazy looking aurora. And people were a little scared, but also really in awe. So the 20 degrees would be sort of around here below the Tropic of Cancer, within the tropics area. It was really interesting because also this caused multiple fires at telegraph stations. So what happens is whenever you have a solar flare that comes to the Earth, it messes with our magnetic field a little bit. It disrupts our magnetic field. That's called a geomagnetic storm. And when you have a geomagnetic storm, or you have any magnetic field that is moving in some way or being distorted, what can happen is you can create electrical currents. And in this case, the telegraph wires that were hung up across the US, they started having electrical currents be pushed through them from a source that no one understood. And in fact, it was from the aurora, from the sun. And so those electrical currents across the telegraph wires actually caused multiple fires at telegraph stations. And if this kind of event, if the Carrington event were to happen today, it would knock out our entire electrical grid. And there would be a lot of havoc, a lot of bad things would happen if this kind of event were to happen today and we were not prepared for it. What's also interesting is that 13 years later, on the 4th of February in 1872, there was another auroral event of comparable strength, but it's not as well documented as the Carrington event for some reason. But what's really interesting about the fact that it was about 12 to 13 years later is because the sun actually has these solar cycles. So the sun goes through periods of strong activity and weak activity. And that cycle is 11 years. So every 11 years or so, you'll have a period of very strong solar activity. And so 12 years later, 12 to 13 years later, to have another auroral event of very strong strength is so funny because it's such a good explanation of the solar cycle. Because another 12 years later, you have a period of strong solar activity, and you get yet another very, very strong auroral event, which is cool. And actually, we had a recent solar storm event, and I mean really recent, like 2 weeks ago. On January 29th of 2022, there was a small coronal mass ejection, and it was estimated to reach Earth on the 2nd to 3rd of February, somewhere in there. But on the 3rd of February, SpaceX launched 49 Starling satellites. Now, see, what happened is that since the coronal mass ejection reaches the Earth, the magnetic field gets a little weird, and the atmosphere actually changes shape a little bit during these events, during these magnetic storms. And so there was an unexpected amount of drag, air resistance, when the satellites got to their altitude that they were trying to be at. And this actually ended up knocking out 40 of the 49 satellites, where they didn't even make it up to orbit. So here's a video. Sorry, it's a bit loud, but okay. Hopefully that's less loud. But here's a video of that. When you see Starling satellites, they're almost always going to be traveling in a train-like situation. That doesn't mean that there's just one that's broken up. They're multiple. They're just in this train formation. That's how they're launched. So you can see a whole bunch of them starting to burn up in the atmosphere, and they end up falling just back to the Earth. And this is not dangerous to the Earth's surface in any way. The satellites are small enough that they'll burn up completely in the atmosphere. However, it is potentially dangerous to things that are already in orbit. So if there were already satellites in orbit, having debris that we can't really control is sometimes bad. It can be pretty bad for those. So yeah, just a few days ago, that is, we lost a whole bunch of Starling satellites to just another coronal mass ejection. And if you were wondering, yes, there was an aurora that day. This is the aurora that was observed in Sheridan, Wyoming, the same day. Here's a picture of it. That's pretty low for the aurora to be actually seen at as well. So pretty cool that we're able to track this coronal mass ejection to not only the aurora, but also to the loss of some satellite launches. Kind of interesting. So now I've talked about the reason that aurorae exists, but I want to talk a little bit about how they work and what we can learn about them. So the most important thing is the colors. They're very obvious when we look at the aurora themselves. And as I alluded to earlier, the colors of the auroras are caused by the excitation of different elements in the ionosphere. So the main colors you can see are red, green, and blue. And those are in order of highest altitude, intermediate altitude, and then lowest altitude. So you're going to see red colors at highest altitudes, green at intermediate, and blue at the lowest altitudes. So the red is associated with oxygen up in the very, very high atmosphere. This is a rare sort of aurora to see, but it's not like that rare. It's relatively common, but not as common as the green auroras. Green is the most common color. Anytime you see an aurora, you are going to see green. That's going to be the main color that you see. Green is also associated with oxygen, just of a slightly different energy level, and then also some nitrogen. The reason this is the most common color is because that's the highest density region of the atmosphere, but also because our eyes are most sensitive to green. So we tend to just see the green a little bit more. And then at the lowest altitudes is the blue, which is from ionized nitrogen. So this is nitrogen that has lost an electron for some reason. There are some other elements, but it's going to be mostly ionized nitrogen at that level. This blue aurora is the rarest color, and you're only going to see that kind of aurora at the very, very highest solar activity. So pretty much you're usually going to see green, maybe a little red, and if you're really lucky, muted. Hello? Okay.
That was me, sorry.
You're good. You're good. I noticed it at least and didn't just keep talking. Okay, so you can also see the UV, infrared, radio, and X-ray aurora emission as well, but we cannot see those with our eyes, so we don't usually associate them with the beautiful pictures that we see. But they do also occur. You can see our aurora in other colors. So here is a picture of our atmosphere. This is similar to the one I showed you before, where you can see the different layers of the atmosphere. This one shows you where the different line regions are, which is nice. So the green lines are here in this intermediate area, and then the red will be on top of that. Try not to confuse the blue line region with the blue sky, but the blue lines are the blue aurora are so rare that you will hardly ever see them. On the top, though, is something I didn't really mention, which is the UV air glow. It's going to be at the top part of the aurora. Now, we can't see UV with our eyes, like I mentioned, but this will be really useful to remember when I talk about aurorae on other planets. Okay, so keep that one in mind. Okay, so here is a video from the ISS where they fly over the southern pole and you can see the Aurora Oval. What's nice is that you can see how the red area is on top of the green area. So the green is the predominant portion of the aurora. And in fact, you can see almost the entire oval as it passes over. And then you can see the like slight red haze over the top, which is pretty cool. Here is a screenshot of a different video, but also from the ISS, where the colors have been enhanced a little bit so you can really see what I'm talking about. So the majority of the aurora is green, and then there's this red portion on top of it, which is really nice. So what can we learn from auroras besides just the elements? I found a really good quote from a paper where he said, auroral forms are like fingerprints, linking optical features to physical phenomena in the near Earth space. So these are like fingerprints to our magnetic field. We can sort of see the shape of our magnetic field doing things. They give us an idea about what's in our atmosphere and at what layers of the atmosphere those things occur at. And it gives us an idea of how solar activity affects our magnetic field. So all of those things are really cool. And one of the main ways we can learn about things, learn about our magnetic field is from the different forms of aurorae, the auroral forms. So I've labeled a couple of them here. Here's like I think these are all in the same place too. So you can see all the different kinds of auroral forms. So here's the glow type of aurora, where it's just like exactly as the name suggests, just a faint glow across the sky. And similarly are patches, which are just slightly smaller glowy areas. These are the most common forms that you'll see, the arcs. Arcs are homogeneous, so they're very smooth, and they're just these big, long arcs across the sky. The arcs can like curve and stuff as well. These just happen to be smooth, sort of straight arcs. And then also there are rays. So rays are like the vertical parts. So I would call like this sort of main part here still an arc. And then on top of that is rays that go sort of upwards in the atmosphere. These aren't the best pictures to show what rays are, but there's like, you can look up a million pictures of auroras. So they're the parts that go sort of straight up in the atmosphere. And there are some funny auroral forms too. As we've learned more about, as we've looked at more auroras, we found more auroral forms. In fact, one of them is called Steve. So this is Steve, the aurora. It was discovered in 2017 by a group of citizen scientists. I believe they were in Alberta, Canada. And so they were allowed to name said aurora. So they named it Steve after a scene from Over the Hedge. So I'll just show you the scene.
What is this thing?
Heather, no!
I'm scared. Me too, Mommy.
Shh, it's okay. It's just what is this thing, Lou?
Well, it's burn. Well, it's obviously some kind of bush.
I would be a lot less afraid of it if I just knew what it was called. Let's call it Steve.
Steve?
It's a pretty name.
Steve sounds nice.
Yeah, I'm a lot less scared of Steve.
Oh, great and powerful Steve! What do you want?
So yeah, they named it Steve. Steve is actually an acronym, which is just the most astronomy thing I've ever heard. So Steve stands for Strong Thermal Emission Velocity Enhancement. So in fact, the name maybe suggests this if you know what all those words mean, but this is actually not an aurora. It's associated with the aurora, and it does occur with the aurora usually. This is definitely associated with a solar wind of some kind, but it's not actually an aurora because they're not formed in the same way. And you may have noticed that when you said, hey, that's not green, because it's not. What it actually is it's a big ribbon of hot plasma up very high in the sky. And it's like, when I say hot, I mean really hot. It's about 3,270 degrees Kelvin, which is about half as hot as the sun's surface. So very warm, really hot. And it's moving pretty fast at 6 kilometers per second. And they know all of this because they actually just sent a probe through it and measured what was going on in there. So it's not actually an aurora, but it's still really cool, and it's associated with the aurora. And it's also a very good example of citizen science coming to pass. And, you know, they may have named it Steve, but at least they didn't name it Aurora Aurora Face or anything like that, because they definitely could have. That's a very real option. Now, however, the picket fence aurora is associated with Steve, but it can be seen without Steve. Now, the picket fence aurora is an aurora, but it occurs outside of the auroral oval. And in fact, it occurs because of this hot ring of plasma warming up the outside, the atmosphere outside of the Steve. And then that atmospheric material cools down and releases this picket fence aurora. So this is pretty cool. 2 new types of auroras already. These were discovered, I believe, in 2017, if I didn't mention that. There's one more too. Almost all recent auroral forms were discovered by citizen scientists, or at least pointed out by citizen scientists. This one was discovered in 2020, and it's called the dunes. So here are the dunes over here, this like wavy thing, and then this is a normal aurora. So yeah, as of right now, I don't believe we really know why the dunes occur. The dunes are less understood than Steve, but I believe what they have theorized is that there's some oscillation of the oxygen abundance. So how much oxygen is in the atmosphere is like it has a wave. There's some oscillation of it, and it makes these almost sand dune like pictures, which is pretty cool. Don't play again. Okay, so now I've talked a lot about what the aurorae look like on Earth. Let me talk just a little bit about what aurora look like elsewhere. So we've discovered auroras on 4 other planets in our solar system, and I'm going to talk about 2 of them. I'm sure you know which ones, but the main one is Jupiter. So Jupiter has a magnetic field that is about 15 times stronger than Earth's magnetic field. And this is probably both because it's huge and massive, but also because it's very turbulent. There's a lot of movement going on in Jupiter. And Jupiter's aurora is very interesting. So here you can see both of the auroral ovals on the north and southern hemispheres of Jupiter. Just to mention, this is the ring of Jupiter. If you didn't know that Jupiter has a ring, I'm sorry to tell you like this, it does. But here is one of the auroral ovals. This is the northern auroral oval for Jupiter, a good picture of it where they labeled the different parts of the aurora. So I want to note that this aurora isn't actually blue. It is in the UV. So if you remember when I talked about the different line regions, it goes green and then red, and then there's a UV region on the top. So we are looking here and observing the UV region of the aurora. So this is the highest region of the aurora. So if you actually looked at Jupiter, if you were able to look at it, you wouldn't be able to see the aurora like with your eyes. We can only see this by using UV imaging. But what's very interesting about Jupiter's auroras is that they actually attach to Jupiter's 4 main moons. So Jupiter has the 4 main moons. I believe it has, I want to say 56 total moons, but it has 4 big ones, the Galilean moons, Io, Europa, Ganymede, and Callisto. So the aurora actually attaches to Io, Ganymede, and Europa here. Normally it also does attach to Callisto as well. So this is some really complicated magnetic situation going on between Jupiter and its 4 moons. They believe that some of these aurorae are powered by volcanic plasma transferring between Jupiter and its moons. So there's just some crazy thing going on where Jupiter is able to communicate with its moons magnetically, and also is able to transfer auroras. There's some auroras that connect to these different moons, which is really cool. And then also Saturn is the other main one that we can really see auroras on. So Saturn actually has a weaker magnetic field than Earth. And as far as we can tell, there is no obvious connection to its moons in regards to its auroras. We also don't really see any connection to its rings, which are a type of moon. Again, I'll mention these are UV images and the aurora isn't blue. But you can see here on the north and southern hemisphere. So that's common of all auroral situations is you're going to have the same auroral oval on the north and south hemisphere of the planet. And here you can see how it changes when we observe it multiple times. And here's what it would look like compared to the rest of the star if you could see it and if it was blue. But one other object that I actually want to mention is that in 2015, July of 2015, we actually discovered a brown dwarf star that is 5.7 parsecs away, or 18.6 light years away, that had an aurora of its own. So brown dwarf stars are not really stars, but they're not quite planets either. They're somewhere in between. There's something sort of in the middle. They don't really emit light like a star does, but they don't orbit a star like a planet does. So this is its own star creating its own aurora in some way. And we observed this aurora with the Very Large Array in New Mexico, which is a radio telescope where they were able to observe this aurora. And they found that it was about 1 million times brighter than the aurora on the Earth, and that it was coming predominantly from hydrogen emission. So that's the element that's causing this light. Now the question is, what is this aurora from? We don't know. No one knows, as far as I'm aware. So this is a fairly recent discovery. 2015 is recent in academia years. So this is really recent, and I just don't think anyone has had enough data to really figure out what's going on with this situation. And we can't really measure magnetic fields directly, so it would be hard to figure out what's going on with that. I do want to mention, because I did forget to mention, that the other two planets that we have observed auroras on are Venus and Mars, but I didn't include them in this talk because there aren't really that many pictures of them, and they comparably are not as well studied as Jupiter and Saturn. So that's why I didn't include them here, but they have been observed. They're different kinds of auroras because they have very, very weak magnetic fields on those two planets. But I want to summarize just the last things, the main things that I said. Everything, the auroras on Earth specifically are almost entirely because of the sun and the solar winds traveling down those magnetic field lines, exciting atmospheric molecules, which then glow in our north and south poles. Also, something I've touched on is that viewing aurora is a phenomenal way to participate in citizen science. If you ever want to do any kind of citizen science, just looking at aurora, logging what's going on, great way to participate in citizen science. And there are all sorts of other ways to participate in science as well. And hopefully you learn that aurora are visible on other planets as well. Before I actually finish, if you watched all of this and you said, well, how do I look at it? What do I do if I want to watch an aurora? Can I just go? The main things you want to do, the first thing you'll need to do is head north. Usually Aurora Oval is around 65 to 70 degrees latitude, so you'll want to go around there. Some common places are like Alaska and Iceland and Norway, although those are kind of far, but some northern Canada as well. You should be able to observe them at. And if you want to be extra super sure that you're going to actually see an aurora, what you can do is go to spaceweather.com, and it will give you updates on recent solar flares, any potential auroral activity. It will tell you where the current auroral oval is and where the aurora will be most likely to be seen. And it can tell you all sorts of other information as well. It can tell you how many sunspots are currently visible on the sun, which is a measure of solar activity. There's all sorts of stuff on that website. I think it even tells you about comets. It tells you about asteroids. Spaceweather.com is really cool and it's free. So this picture here, if you were curious, is a picture of the November 4th aurora from that big coronal mass ejection that happened in November of 2021, where you can see just the pure extent of the auroral oval. Just for context, these are the Great Lakes, right? So this is gigantic, covering so much of the Northern Hemisphere. And with that, I want to thank you all for listening, and I can take any questions that you might have. Hopefully enjoyed.
Thank you, Courtney. I really enjoyed that. If we could all have a virtual round of applause for our speaker tonight. I'm trying to find my my applause right there. So I know it's a couple of you have put questions in the chat for Courtney, and if any of you do have questions for our speaker, please feel free to put them in the chat. But I'm going to take the host prerogative and ask the first one. What is your favorite Pokemon?
That's been the AOT question. I love that so much. I feel like I have to plug my little guy Wooper, who sits on my desk. He's a great little dude, but I mean, I also gotta go with like Squirtle. I got a Squirtle tattoo.
Ah.
Yeah, that was what my dad used to call me. I have some other little Pokemon, but his little smiling face is so cute. So dang cute. So that's gotta be my favorite.
Yeah, I am a Mr. Mime fan.
Oh, you know what? Actually, I've been playing Arceus and I've also fallen in love with Cleaver. So that's a good one too.
Okay. Well, let's see. We have, I think our first question is from Vikram. And he asks if auroras are caused by, I think he says, I'm assuming auroras, are caused by solar flares, then are they harmful to humans and life on the Earth?
Not really. They're not harmful to us because that's the point of our magnetic shield. So let me get back to this plot. I know I'm going kind of fast, sorry. But it's this one. So our magnetic shield right here, that's what's actually protecting us from the most harmful parts of those solar flares. Generally, they're not very harmful to us. And the aurora itself is definitely not harmful to us because the thing we're actually seeing is not the material from the sun, it's the effect of the material from the sun. So the aurora itself is definitely not dangerous to us. And the material that comes from the solar flare that actually makes it to the poles is relatively minuscule. There's not actually that much material that makes it to the Earth. So no, it's not dangerous to us. Although if we got a huge solar flare, that would obviously be dangerous to us, but for different reasons.
Aiden asks, why are auroral ovals ovals? And why is the oval on Jupiter off center?
Okay, good question. So the reason for that is because our magnetic field is not symmetric. So here's actually a good example of that as well. See how these magnetic field lines are sort of squished on this side and they're really long on this side? And you can see even here that the magnetic pole, the north and south pole, are not like a straight line. They're kind of pushed towards the back of the Earth, away from the Earth. And that is just because of the way that the solar wind pushes on our magnetic field. So normally, since there's a constant solar wind, it's always shaped like that. But when there's like a really strong solar flare, it gets messed up a little bit more. But generally, it's because of the sun's solar wind pushing our magnetic field away from the sun. It's the same reason that comets have tails. So the comet, if you see a comet, its tail always points away from the sun. That's this exact same phenomenon where the solar wind is actually pushing that material away from the sun.
Very cool. Aiden also asks, how did they find out there was that aurora on the brown dwarf?
They looked, to my knowledge, I didn't read the actual paper where they discovered it, but to my knowledge, they were looking at it with the Very Large Ray, which is a big radio telescope. I don't know for what reason they were looking at the star to begin with, but I imagine that they just saw a lot of emission in the poles of this brown dwarf and then did some studying on what it was and found that it was associated with hydrogen wavelengths that hydrogen emits in.
It was a serendipitous discovery, probably.
I think so, probably.
Makes sense. So Sam and I have questions about Steve. My question about Steve is, so is this not a singular event, but an actual phenomenon that comes and goes, or is it always there?
I believe that Steve is not uncommon, but not like, it doesn't happen every time. But it's not uncommon either.
Okay. Sam was asking if, how are they allowed to name this particular object Steve? So if Sam were to discover something similar, how would he get to name the object himself?
I think that what happens is that since the citizen scientists discovered it, they were allowed to name it, which is generally how it works. If you discover it, you get to name it. Although asteroids have some different naming conventions. But I believe they were at a conference. If I remember correctly, they were at a conference where they were discussing this phenomenon and what it could be. And some citizen scientists were like in the conference discussion talking about it. And we're like, let's name it Steve. And then everyone was like, haha, yeah, Steve. And then they mentioned the over the hedge clip. And then I think some astronomer came up with the acronym and they decided to just keep it.
That's about right.
That's about how academic or astronomy conferences at least actually go. So makes sense.
Well, I know that for astronomical objects, the AI or the International Astronomical Union, the IAU, has its fingers in what things get named how. But do you know, Sam asked, do you know what agency regulates, say, atmospheric naming?
I think it was like it's like the IAU, but I think it might be the IGU, the International Geophysical Union.
Okay.
Something like that. I found it, if you like actually look up Steve Aurora, there's a pretty good Wikipedia article on it. And it has a little story on how it was named, but NASA calls it Steve. So it's just Steve now.
Awesome. So Justin asks, some people say they can hear Aurora. Is that even possible?
I don't know. I would think maybe. I have a bit of a biased opinion because I have been told that it's not normal to be able to hear lights. So apparently I have, some kind of weird hearing, but I would think that you probably wouldn't be able to hear the aurora as much as you could maybe hear the crackling from maybe like the cosmic rays from the sun. That would be my guess. I don't know. I've never seen an aurora in person, so I couldn't tell you if I know, and I wouldn't have known to look that up, but I will be looking it up after this to see if we can hear it.
I suspect because if aurora are tied with synchrotron radiation, then there are certain wave bands that you can hear it with a radio. Not like on the FM band, but because you can listen to Jupiter.
Yes.
And so if it's a similar sort of, if it's a similar effect, then I think that's where you could hear an aurora is by listening.
Yeah, certainly if you hooked up like maybe like an AM radio, you could certainly hear it that way if you like converted those radio frequencies into sound waves. Definitely.
Yeah. Yeah. That's I'm also going to Google that. I am curious.
Me too.
What frequency you'd have to tune into in order to actually hear an aurora. Yeah. All right. Are there any other questions for Courtney? If not, then please give her another virtual round of applause, and we will be moving on to the second portion of our night. We will be using the telescope, hopefully, assuming everything went right today. We will be transitioning. So, M, are you with us?
Yes, I'm here now.
Okay. Courtney, if you'd like to stick around and watch, feel free. But if not, then it was great having you here.
Thank you. I'll definitely stick around for a few minutes, but I'm trying to catch AOT.
Of course. All right. So yeah, M, how is our telescope doing today?
Right now, I think Dr. Pavchan just set it up.
Yeah, hi. Just to update everyone, we've been frantically trying to adjust the pointing model of the telescope. Let me just do we just have Em and Rob on tonight?
Yeah.
Okay, sorry for the logistics live, but just so you all know, we have supposedly a mostly working pointing solution. I don't trust it at the moment, but we're going to go ahead and we do have some clouds that have been rolling in, some thin clouds. So Em, you could start with the video feed, and then we did just take an exposure of the moon. So I'll let you take over from here.
Right.
Great talk.
So I share my screen. Can you see it now? Okay. So, all right. Welcome to the GMU Observatory Tour session. The telescope just recalibrated. Hopefully we can point at something today. So here is some videos recorded by 4 cameras on our observatory. The first one is to look at the telescope. This one is inside the dome. This one is inside our control room, so we know who's inside. This is where this computer is. So basically, I just signed into this computer and share the screen for you. I can control. By doing this, I can control the telescope remotely. Here is a video showing the whole dome. You can see the telescope inside. We want to monitor how the dome moves relative to the telescope. And finally, we also place a video underneath the fork of this telescope just to see some mechanism when we slew the telescope. Okay, so I think we can see the moon today. Yeah, right now we're pointing at this region, very close to the moon. So let me slew it.
It was already on the moon.
Oh, okay.
That's how far the pointing's off. So you might want to go back.
Oh, all right. So this is the program called Skyax. It's the program that shows the night sky. We use this to tell how the telescope should point at a specific region of the sky. You can command it to slew or move to the target. And here is XMJL, a program that connects to the CCD cameras of the telescope. It allows us to change the filter. For example, this is the moon taken by H-alpha filter, which is a light in red wavelength. And we can control the exposure time here, the amount of the duration of the time that the CCD exposed to the night sky. And we can see here, this is the image captured by CCD from what it's pointing right now. You can see the moon. Tonight we have full moon, luckily, so we can see almost every detail on the craters and bright craters, some array on the moon. Okay. Do you have any suggested object that we should look at tonight, Dr. Parks?
I think you could go to the Orion Nebula next. If the pointing's working, but I'm a little bit skeptical it will.
Okay. So,
definitely, things did not go well tonight. Oh, we also have some clouds. Neptune is up tonight, or sorry, Uranus is up tonight. Unfortunately, Saturn's already set, Jupiter's already set. Mars hasn't risen yet, so it's not a good night for planets tonight. But yeah, you could try slewing to Orion Nebula.
So I can find the target from here.
Orion Nebula? Oh, yeah.
Where I can slew, telescope moves. So you can see here the motor moves and the whole telescope moves accordingly. This is from where we can see it from the outside. Let's focus on this one then. It moves to the west side of the sky, and the dome moves according to the telescope, so that the window aligns and allows us to look at the night sky. So from here, you can see there's another motor mounted on this telescope. And so we have one motor underneath this fork that allows us to roll the telescope, and this is like pitching. We have two axes for what we call right ascension and declination. It's the coordinates of the night sky. And from here, you can see it a little bit. We have some cameras and eyepiece, maybe barely see it. This is where those things were mounted. Right now, we hopefully be pointing at the Orion Nebula. So, try capture.
Might want to do more than 5 seconds, but 5 seconds. For those of you in the audience who may be some of my students who are visiting an observatory, a few things that you'll want to know about this telescope is that it is a RC Cassegrain optical design with a 32-inch aperture.
Okay, I think we're off.
Yeah, all right, so we're getting some clouds.
Yeah, trying the clear filter or the R filter for now, just to see how bad the clouds are.
And do you have any suggestion where should we move?
Until we actually see what you're looking at, I have no idea.
Okay. So let's try this.
Because you're
So
seeing
now
some stars, but it's not, no, the exposure time is not long enough.
So now I'm exposing clear filter with 10 seconds in 10 seconds.
I would just do medium. Instead of manual, do medium. That'll get you in the ballpark.
Yeah, so I think our morning solution was not a success. I have to repeat it.
All right. So I think maybe we try pulling out the pre-captured file then. Okay. There is a question or suggestion on the chat about planets. So currently, the most spectacular planets we can see is Uranus and Neptune. Saturn and Jupiter are already setting below the horizon. This is the sun. So if this is in early December, we will still see those planets. So here is captured images of Jupiter and Saturn. You can see the Jupiter's moons lying in this plane. So there are 4 moons actually. This is maybe a background stars that come into the field. This image allows us to see some stripe pattern of the Jupiter. This is the Saturn with its ring. I think this is taken in 2020, the conjunction event, when they closest together when viewing from the Earth. This is the moon. We already seen that in the Maxim DL program. Here's what Neptune should look like from our telescope. It appears to be pretty small from the viewing from the Earth, because it's the farthest planet, except if we don't count Pluto, it's the farthest planet we can see from the Earth.
Always count Pluto as a planet.
Yeah. Can we see Pluto right now? I don't think we can.
I don't know. I don't even know if Neptune is up, but it could be. But I think it would be too, amount of clouds out. Might be too cloudy to see. Definitely show them what the Orion Nebula would look like.
Yeah. So to go to Orion Nebula. So this is what we usually see during this time of the year. It's called Orion Nebula, located in the constellation Orion, so around this region. You can see with your naked eye, actually, but we cannot actually tell the color, because our eye, in the nighttime, our eye cannot perceive much of color. You can see mostly black and white. So Orion Nebula is a diffusive nebula where newborn stars are located. Just the region where it's most, where it's brightest is where the stars are most clustered. Two of them. This one is called Eagle Nebula, recorded in H-alpha filter, so it's in red color-ish. But from our telescope, we measured only the intensity. That's why it appears to be black and white, because we haven't assigned any filter to this image yet. This is Horsehead Nebula, another nebula taken from our observatory. It's composed of the background diffusive nebula and dark nebula, blocking the view of the background light, and it looks like horse head. This is recorded in H-alpha, visual, and blue filter. So there are three filter images combined and assigned to a specific color. I guess H-alpha is assigned to red color, visual is for green, and blue filter was assigned to blue. So with those three colors combined, we can produce this kind of color image. Actually, most of the color images we showed you here is a combination of multiple filtered image. Okay, this one is called Dumbbell Nebula. It's a planetary nebula. It's a remnant of a exploding star. I cannot really tell if we can see the center, but usually this kind of nebula, we can see the white dwarf at the center. It's the remaining of the exploding stars. I think the obvious one is Crab Nebula. Have it somewhere.
So for example, there are a couple of questions about the namings of things. And so what Em was showing you were some nebulae. Well, let's take this for example. This is M51 or Spiral Galaxy. So the proper name of this object is the Whirlpool Galaxy or M51. And what the type of object you're looking at is a spiral galaxy. So I just wanted to clear that up for some folks in the chat.
Okay. Now I'm showing you some galaxies. This is called Whirlpool Galaxy. It's actually composed of two galaxies. You can see this bigger galaxy and the smaller. They are actually merging within a few million years. They will be completely combined into one single galaxy, and they may not end up being spiral galaxy like this because of the gravitational pull changes its shape and how we can view it from the Earth. This is in my opinion, this is the most spectacular galaxy we've taken. This is called Fireworks Galaxy. I'm not sure if it has to do with 90 minutes exposure time or not. But yeah, it's another type of spiral galaxy. You can see a small ridge here and here, which is actually some dust particle blocking the light. Okay, let me see what we usually see during what we usually see in the night sky during this time. Usually in this time of the year, February, we can see Orion constellation, and we can see the brightest star in the night sky called Sirius. This is my favorite star. When viewing with Betelgeuse, and this is called Procyon, another bright star, it formed a winter triangle. Yeah, used to locate. We can use this to navigate the night sky. We can also see Pollux and Castor. I'm sure Dr. Plapshan also used this as a target to calibrate the telescope earlier this evening. It's there are the bright star in the constellation Gemini, one of the zodiac. Can we from the chat? Can we see the Andromeda galaxy? Yes, we think we can see it somewhere here in the sky. Search for Andromeda galaxy. Yeah. Let's see it. It's not appeared, doesn't appear yet. Yeah, but we should be able to see it. But it's pretty faint. We can see it with our naked eye. Not sure if we have some pre-recorded.
I certainly have taken images of it, so it's gotta be. I keep meaning to actually go through our images and organize them.
I don't think we have Andromeda recorded because the field of view is pretty wide. If I'm correct.
I've been trying to, yeah, I'm trying to take a mosaic. Let me see if I can figure something out here. How do I put this?
So the question from the audience, where it's pointing right now. So right now the telescope, they program things that telescope is pointing at the Orion Nebula, but unfortunately we have some problem with the calibration. It's off by some degrees or some arc minutes. It's pointing to somewhere, maybe here, and it's pointing to somewhere empty, the sky. So this is what we see when we capture from the camera. Okay. So I don't think we have Andromeda saved yet.
I've got that in a second. Let me respond here. All right. Let me share my screen. Take it over. Boom. That is the Andromeda Galaxy, or an image of the Andromeda Galaxy that I've taken.
It's nice.
So this is, yeah, so as you're saying, the Andromeda Galaxy is huge. And so what I've done is I've taken basically 4 shots of the Andromeda Galaxy, and I want to mosaic them together. This is only but one corner of the Andromeda Galaxy. So, but hopefully I will find the time to actually finish that. But I will hand it back to you.
Okay. So yeah, let's see again. So yeah, that's the example of an image larger than our field of view. When viewing with naked eye, I think it almost looks like a cloud scattered in Andromeda constellation. And what I'm showing you now is Betelgeuse. It's one of the bright stars inside Orion constellation here. It appears to be orange or red. This one is taken when a thin cloud blocks the Betelgeuse. So we can see some distorted shape. And so instead of having nice round shape, it becomes a little bit oval. So that's one of the effects of the clouds. We don't have much about stars too, but at least show you cluster 13. So this is a star cluster. I believe it's open cluster. Usually when we see constellation in the night sky, it's just how we see stars from the Earth. They are not actually close together. Like this asterism or the pattern of stars are called Orion belts. Orion's belt. So the Orion's belt composed of 3 stars, but they're not actually close together. It's just how we view from the sky. But for the cluster like this, it's a bunch of stars forming probably around the same time. They tend to have similar age. And we can see it as a sky object. Usually we'll see it as a bunch of white dots with our naked eye. Since our talk mentioned a bit about the sun and the corona, we also have some pre-recorded picture of the sun taken by our solar telescope. Not this 32-inch telescope, because we cannot point this at during daytime. The sunlight can melt the internal part of this telescope. We need a special filter to screen some light off. With this solar telescope, we can see some solar flare and solar activity on the surface of the sun. See some sunspots. Oh, I think that's probably the dust. But we can see solar flare and some grains. Maybe it's not obvious, but we can see that the surface of the sun is not completely smooth. This is one of the most of this corona. No, not corona. It's the solar flare. We have some captured video too. Not sure if we have that took this recently. There's a student club called Photo or Friends of the Observatory, capturing the sun during daytime. They have very nice solar the sun image of the sun. Okay.
They're going to be taking this. They're going to be taking that telescope out for another test drive. I think this coming Sunday.
Oh, okay. So if any of you want to join them, you're allowed to. Okay. So unless I can point it to some region of the sky, I think we that's all for tonight. Should we try some other target? What do you have any suggestions?
I think we're probably good for tonight. After this, I will try my hand at doing a pointing model and seeing if we can get that sorted out later this evening.
Okay. All right. So if you have any question, feel free to put it on the chat. If not, we can call it a night. You're welcome. Have a good night.
Thank you.
Bye.
The signature is a screenshot. If you guys are still there, you still have a question. So, all right. Bye all.
Bye.
And this.